Today is Koji Ohkitani, who will be telling us about numerical and analytical study on the asymptotic equation for the deformation of vortex lattices.
Okay, thank you very much, Mr. Chairman, and thank you very much for the organizers for the kind invitation, and thanks for the audience for remaining until late to the final session. You do deserve reception. And today we are going to talk about under this title, and this is a joint work with one of my students, Pfizer Al-Salti from Sheffield. Okay, and the keywords are two-dimensional turbulence and reconnection and blow up. And the essence of the main part of this talk is a study of this nonlinear partial differential equations, mostly numerical one. But before we get to the main part, I've decided to give or include two introduction or motivations as part 1 and 2, which is about 2D turbulence and vortex crystal. And another one is topological study of two-dimensional turbulence, because this conference is specialized in this element. And then we move on to the main topic of that equation for the deformation of vortex lattice and study its blow up by numerical methods, and hopefully end with summary. And here is an example of formation of vortex crystal, and this was done by that author in 1999. One is from laboratory experiments and the other is from numerical experiments, and I don't recall which is which, but my best guess is the above one is from the laboratory experiments and using magnetized electron columns. This technology is based on the following principle, which is an analog between 2D Euler equations and guiding center plasmas, electrons. Okay, and because of this analogy, they can actually realize formation of vortex crystal experimentally. When you do experiments, numerical experiments, you have to add background rotation, and then if you are lucky, you may find a number of isolated or localized vortices forming a group, and they will be happily dancing for the time being. This is called vortex crystals. And if you have many vortex crystals, you may fill up the whole space or plane by them, and this is called vortex lattice. And this is a topic we'll come back later. And here is another topic. This is a topological study of two-dimensional turbulence, and we are going to simulate 2D Navier-Stokes equation using standard vorticity form, where psi is a stream function. As we all know, the underlying potential problem for this problem is Poisson equation, and hence the relevant Green's function is, of course, a logarithmic function in 2D. And by the way, this is the stream function we need when you form point vortex system by discretizing omega like Dirac mass. And we are also considering another system which is called Chani-Hasegawa-Mima equation that appears in plasma physics and also in geophysical science. And this only difference of these equations is that the potential problem is slightly modified by one constant, lambda, which may be regarded as the reciprocal of Rossby radius. And for this reason, the Green's function corresponding to this problem is modified like Bessel function, k sub naught. It behaves like a logarithmic function near R0, but away from it, it decays exponentially. So this is a screen potential.
There must be a lambda in this potential.
Yeah, you are quite right. No. This
This
definition is so. It's misleading. Sorry about it. Thanks. And we are going to study, pardon? It's Macdonald function or modified Bessel with an imaginary argument. Okay, and standard understanding of two-dimensional turbulence is coherent vortices appear spontaneously out of random media, and they will stretch vorticity contours between them. And they would merge as time goes on for the decaying case. And in this sense, reconnection of contours of vorticity is very important. And so it is of interest to study or characterize this process by using some topological methods. And back in 2001, when Keith Moffat visited Japan to give a seminar or talk at another IUTAM symposium, he proposed some kind of ideas. And the point is, consider critical points of vorticity, which is given by this condition. And if you have N0 minima, N1 saddles, and N2 maxima, standard Euler's index theorem applied here, and it says the total of centers must balance with the number of saddles. This is purely kinematical constraints, nothing to do with dynamical equation. And so we may follow using dynamical direct numerical simulation evolution of these numbers and try to characterize the flow. And this was similar idea was taken up by MHD people like this one. And here on top of these critical points, we would apply another technique which is called surface networks. And here it was developed in the area of geographic information science. The people who are interested in generating maps efficiently. So they need to find a way of drastic reduction of information out of huge data. And one way to do so is to build surface networks, which is made up of two things: nodes, this is of course minima, saddles, and maxima, and also edges. Edges are curves starting from each x point and leading to one of the maxima or minima following the steepest gradient. So we have generated this kind of networks using our numerical simulation. And here is, before that, here is numerical verification of Euler's index theorem. It is not terribly remarkable achievement, but we should do that because we have to be sure that our interpolation algorithm is doing a good job in identifying critical points. So the solid line is for the sum of the centers, and dashed is for the saddles. And basically, they are doing a good job. And we have some discrepancy, but if you pad the flow field onto a final mesh, we could achieve better accuracy. So it is satisfying. And I will show you some highlights out of this effort. Here is still faint. 2D Navier-Stokes equation at late stage, somewhere around here. We have coherent vortices. On the left, we see it's too faint, but contours of vorticity together with the location of maxima, circles, and sharps for minima, and x for saddles. This is the standard picture of two-dimensional turbulence. And if you do the surface network starting from each x point, you observe this, and it nicely visualizes how those coherent vortices stretch vorticity of contours of vorticity at a distance. This is a standard or traditional picture of 2D turbulence. And when you do the same thing for CHM equation here, again, I overlay the contours of potential vorticity and the location of critical points. We do have, or we do observe, a number of a little bit smaller structures. But when you do the surface networks, there is a remarkable difference from the previous one. In the sense, here the potential is screened. And hence, those guys, the coherent vortices, cannot stretch vorticity contours, potential vorticity contours at a distance. And they are kind of cut off. And hence, if you do the surface networks, we do see formation of lattice rather than this one. And hence, with this technique, you can distinguish the different character of potential problem from 2D Navier-Stokes and 2D Charny-Hasegawa-Mima equations. And that's one of the results from our recent research. Okay, and now we are coming back to the main topic of the vortex lattice, and we are going to consider the following differential equation for phi, which is given by Monge-Ampere type operator on the right-hand side. So if you consider the Hessian matrix of this scalar function, if you take trace, of course you get heat diffusion equation. But if you go for another characteristic, you would get this Monge-Ampere operator. And this was derived by Smirnov and Chukba back in 2001, and also this paper. And this phi denotes a kind of potential for the deformation of already formed vortex lattice. And note that the right-hand side is basically proportional to Gaussian curvature of the stream, the Gaussian curvature of the surface phi. So we've got a steady state for a developable surface. And if I start elaborating on how to derive this equation, I would use up my whole time. So I will give you some essence only. And the sketch of the derivation is consider point vortex system whose interaction is short range, just like we had in the CHM equation, and do the coarse graining on the triangular lattice, something like this. And consider long wave perturbation, and then you get that equation. Okay, so this is a very brief. And before showing some numerical results, if you consider axisymmetric case by moving on to spherical polars and dropping angle dependence, you get a simpler equation. And by a standard method, you may seek a self-similar solution that can blow up in finite time. And we do find some examples quite easily, like this one. But the point is, this depends upon R explicitly, so that it doesn't belong to L2. Whereas, because this phi is responsible for the perturbation of the vortex lattice, it is natural to think of perturbation which is localized in space. And it would be better for phi to be in L2. So our question is, if you start from initial data, which belongs to L2 and smooth for this equation, can we find singular behavior or not? That's the question we are interested in. Okay, so we are going to work out some numerical experiments on that equation using standard Fourier spectral methods with these resolution, and these are the parameters. And here we add viscosity and compare it with the implicit case. On top of this viscous diffusion, we apply a filtering method. When the phi in the Fourier space reaches round-off level, we put it to be 0 at each time step. And we watch the evolution using Sobolev norms, H norm, H naught, energy, and H1, H2, and so on. And our initial data is a very simple one. It's a sine x, sine y with some amplitude. And this is the evolution of the Fourier spectrum of phi with this A. As time goes on, it will develop or excite higher wave number components. And at some point, we would observe a funny bump here, like this. And I thought, when I saw it for the first time, I thought it was kind of a numerical artifact. Later, we found this is not the case, and this is a genuine mathematical property for the reasons I will describe from now. And in the case of Navier-Stokes equation, we cannot prove global existence of smooth solutions for general initial data or general viscosity. But if you consider very large viscosity or very small initial data, you can prove global existence. Whereas in this case, if you change A, by the way, this will break down at finite time, very close to t30. And if you change this parameter or amplitude A, if you make it smaller, you have to wait longer until breakdown takes place. But the point is, this numerical breakdown, the time of numerical breakdown is approximately proportional to h to the minus p. And hence, if you extrapolate this trend onto the small a, even if you make a very small, definitely you will get breakdown. So it is not like the Navier-Stokes equations. We cannot ensure the breakdown global regularity for the small initial data. And the reason is, unlike Navier-Stokes, we have no energy inequality. Phi squared is not guaranteed to decay. And here is an evolution of higher sub-F norms. This is log linear, and this is the enlargement, H3, H4, H5, and H6. It's very difficult to distinguish which goes singular, but H3 is very small until the end, whereas H4, 5, 6 apparently goes singular at finite time. So we would think or interpret if the sub-F norm H4 or higher order than that would go singular in finite time. And some fields. If you plot phi, it's boring. Nothing changes. If you take Laplacian, you would observe some asymmetry here. And if you take third order derivative, we have observed spiky structure forming. And double Laplacian fourth order derivative, it is prominent. We have a very high amplitude. And again, you plot the maximum values of first, second, and third, and fourth order, then you will see the first two would remain okay, but the third and fourth order would break down at the final stage. So these are the characteristics. But if you take the weighted spectrum by multiplying k to the 8 or even k to the 12, we do see the peak here, bump, but it is still well resolved until late stage. So that's why this bumpy structure is genuine. And in the physical space, if you plot the third order derivative or fourth order until the end, at the final stage, we see these undulations, spikes forming very rapidly. And that is the reason why we have this sharp increase in the maximum values. And by the way, this defines a characteristic wave number. And actually, that wave number corresponds to the radius of this core, and consistently. So our numerical results suggest that finite time breakdown takes place in such a way that phi remains H3 but does not remain in H4. And this is totally consistent with mathematical constraints starting from coming from Sobolev embedding. If you write down a series of Sobolev inequalities for second, third, and fourth order, first one is kind of it's not very sharp, but the second and third imply H5 and H6 to be singular. That is consistent with our numerics. So this is a summary. And after doing some topological characterization of reconnection, we have discussed one equation derived by Smirnov and Chukuba and do some numerical equation. And they are the reference for the 2D turbulence. And finally, outlook is it would be nice to have an equation for the point vortex system in doubly periodic domain. And in the case of standard 2D Euler, which is 1 over Z kernel, this was done by Tokachenko and some people in this audience. But our question is, if you modify this kernel to the screen potential, what would be the right equation for the point vortex system? This is a Fourier representation of logarithmic function using box normalization. We have two limits. One is go to zeta function, elliptic function, and this is a Bessel function. So it might be a combination of these two. I don't know how, nowadays not many people have deep knowledge on special functions, and I don't have either. And if you have some, just come my way after this seminar. That would be excellent. Thank you very much.
Questions? I have a quick one.
Yeah.
Am I correct to say that an irrotational flow has mean curvature 0 according to this in your description?
Not in my description. I mean, you are talking about their paper?
I don't know, when you wrote the evolution equation, so phi xx plus phi yy is the vorticity, right?
No.
No.
Phi is a potential for the deformation of the applied to the vortex
I think
lattice.
phi was used for a stream function earlier.
No, it's not like
Oh,
that.
sorry. So then my question is not interesting. Are there any better questions than this one? All right. If not, then let's go to, there's one.
We showed some comparison between Napier-Stokes and Hasegawa Mima simulation. I think there must be some scaling parameter that can make that difference because the Hasegawa Mima is just a slight modification of the Laplacian operator.
Yes.
By the parameter you set the epsilon or something.
Uh,
So that must appear in the comparison. So my question is there any typical value for that?
the point is, for the standard 2D Euler equation, lambda is 0, so it has a long-range interaction. And if you have a non-zero lambda, even if it is small, it's cut off the potential. So this is qualitatively different.
But there must be some, the scaling for the dimension size or something like that.
Scaling of dimension size.
I mean, the dimension of the domain.
Yeah, if lambda is bigger than the domain, clearly it's going to look more like Euler, I guess.
Because if you consider a very small domain, then that small shift of the spectrum doesn't matter.
Here we work on R2 in the whole space. And for numerics, we do periodic boundaries. Yes. Now I get to understand your point, and I would like to discuss maybe over a glass of wine or something like that.
All right.